This new video in which we're going over a basic deep learning training flow. And this is very fundamental, very basic. If you want to go deep into deep learning, that's pretty much something you should know inside out. It doesn't hurt to practice it for once in a while. This is really basic stuff about how to train a neural network. We're going to go through how I'm creating my own little sample data set. This is so you don't have to download any data from anywhere. We're going to have everything self-contained in this Jupyter Notebook. Then we're going to construct a multi-layer neural network classifier, select optimizers and a loss function, and go through the training, how to evaluate, and then set everything up for hyperparameter tuning. This would be the next step. Once you have a flow set up, you can tune the so-called hyperparameters to make your training more effective. So I'll start by installing a few dependencies. So we'll use PyTorch for everything around deep learning, matplotlib because I'm going to make a few graphics, and scikit-learn primarily for using the function to generate a confusion matrix. So that's something to establish our trained classifier's effectiveness. So the mock data that we're going to generate here is 2D Cartesian data, xy coordinates. I'll put that all into the variable x, and it will get labels, each of these points, 1 if it's inside a circle of radius 0.5 around the center, and 0 if it's outside. And down the road, we want to have the data stratified, meaning we want to have equal number of labels 1 as well as labels 0. This is important for good training, so we're going to make sure we have that. So in this function here, I'm going to create mock data. The two parameters I'm passing are the number of records that I want to generate and the number of feature, meaning the number of coordinate dimensions. So in our case, this will always be 2 because we want to create 2D data, but this function is actually more general. We could also do it in n-dimensional space, but either way, just for this example, it's going to be 2-dimensional. And we're using NumPy's functions for generating random data of a certain shape, so n records and n features, and we're going to subtract the value 0.5 from it. So these are all numbers between 0 and 1, and I will want to center the data around the 0.00. So now the labels will be applied by this function here. So it's essentially if in that array of x, the points have a distance from the origin that is less than 0.5, then the label 1 will be applied, meaning it's within the circle, and 0 if it's greater than 0.5, then it's outside the circle. So what this does is the typical Euclidean distance, the square of all coordinates of all records, the sum of that then, and then again the square root. So nothing new here. So we're going to create that, and here I'm going to create 10,000 data points, just like that. And I want to scatter plot them. So each of them, for each of these data points, the first and second coordinate, and I'll apply the labels accordingly. And what we get here is exactly that. So label 1 is yellow for inside the circle, purple is outside the circle. Now I mentioned we want to stratify the data. So we want to make sure in our data set, we actually have the same number of purple points as we have yellow points. So that's what we're going to do next. You can look up the details of these two functions in the code. As mentioned, I usually put my code onto GitHub, so you'll find that in the description. But just here, I'm going to do a very targeted selection, random selection by label to make sure I have the equal number of data points for each label. And once these two methods are ready, I can do that, and I can, for example, get 200 data points of axis and label. And if I plot that again, then we see exactly that. So now you can kind of eyeball it. We have the same number of yellow points as we have purple points. So this is the perfect ratio for doing training on this. In PyTorch, when you do deep learning or training in general, what you usually want to do is you apply data sets. So you make a class that extends the PyTorch class data set, and I usually pass in my data, convert them into Torch tensors, and all you have to do is override these handle methods here. Get item, that is usually what is invoked when the batch is called. So it's basically just passing the index into the row indices of the tensors. Also, if you want to just get the number of data points, you can call the len method, and that will give you the number of records in each of these tensors. So this is a mock data set. We said and features will always be 2. In our case, I'm creating a 10,000 data point training data set and a validation data set of 500 data points. So I'm running this. It just takes a few seconds, and now I have the data in these data set objects. Next, we're going to build our neural network classification model. And so it's a linear neural network, also known as a multi-layer perceptron. And it has a variable number of hidden layers. So that's everything between the input and the output layer of the neural network, and a certain number of nodes per hidden layer. Also, we're going to be using the rectified linear unit activation, and optional, we can decide to use batch normalization. So this is something that's usually used for making the training more smooth, faster, more effective. So that's something we can also have as a part of the architecture here. So as we kind of initialize our multi-layer perceptron, the number of feature, that's the number of inputs that go into the network. The number of hidden layers is a parameter. The number of nodes per layer. This include batch norm is a Boolean flag. So depending on whether we want to do batch normalization or not. And all of that will be put on device. So if it's, for example, running on GPU, you want to run that on CUDA. First line is we're calling the init method of the superclass. And now we add all these layers as properties to the class. So the include batch norm, that's just a flag where we're setting that here. The input layer is the first layer of the network. So that's a linear layer, takes in end features and outputs the nodes per layers. Also for all of these layers, we put them to the device right away. The hidden layer, now this is a list of linear modules mapping the number of nodes to the number of nodes put to device. And we do that exactly the number of times that we want to have hidden layers. If this flag here is set, then we're going to also maintain the batch norms. Same thing, it's a list of 1D batch norms for the number of hidden layers. And also an output layer. And there will be nodes per layer to 2 outputs. And these outputs are 0 and 1, depending on the label it's going to output. So when we forward run this multi-layer perceptron, we put in a tensor x. The x goes to the input layer, then the rectified linear unit. So see here, this is not actually a layer with any parameters that we have to maintain. So this is really just one mathematical function. There's no parameter that needs to be remembered or tuned or anything. So we're just gonna call this function here. And then for each hidden layer, we're going to set our results to that. If we do have batch normalization, we also apply them here. And this is after each layer. We do the reload function after each hidden layer. And in the end, we're also going to then apply the output layer. This is the normal forward. We're going to use that during the training. If we then in the end actually want to predict a label, we have to do one more thing. So we're going to apply the model itself, and then we apply the softmax function to the outputs that give us the probabilities for each of these labels to be true. And then we're just applying max function to find out which of the labels actually the prediction is. And that's going to be the output. So I'm just gonna run this cell to have the model built. And now I have these two functions here to evaluate the model. And that's something I want to do before, during, after the training. So one is called compute dataset loss. And what it should do is it computes the loss for all the data points for a given model that I pass in. So pass in the model, the loss function, the data set. In our case, this will be the validation data set. And then also we're going to put that right onto the device. In order to do that, we put the model into evaluation mode and back into train mode, as well as we run it without gradients. All these is so that we actually don't maintain gradients here, because we just want to forward apply the model and make computations. This is not part of the actual model training optimization. Then we're going to transform the data set into a data loader with a given batch size, run through the batches. By that, we apply the model, compute the loss, and add it to this cumulative loss. And in the end, we're going to divide it by the number of data points. So that's one of the evaluation functions. And we also want to just display a confusion matrix. So confusion matrix basically tells us how many times did we correctly predict the label, how many times did we think it was in the circle, but it was actually outside the circle, and so on and so forth, right? So we'll have a 2x2 matrix in our case. Same thing, we're going to run it in no-grad evaluation mode and run our predict method on the model, and then pretty much return a confusion matrix of actual versus predicted. The training loop itself, this is where we put everything together, right? And what I like to do is make that a function that is also parameterized by these so-called hyperparameters. So for example, how many epochs do we want to run the training for? What's the learning rate of the optimizer? The batch size that we train on. So that also has an impact on how effective and fast the training can be. The number of hidden layers in the neural network. So now it goes into architecture. Also the number of nodes per layer. Also, if we want to include the batch norm. So all this goes into, these two things go into the architecture of the neural network. And then this one is more a observation feature. So this is the number of epochs at which we always want to have a printout on the current validation loss. I'm going to establish what device is going to be used. So this standard line gives us the CUDA if we have a GPU available, otherwise we'll train on CPU. Then we build our model. This is our MLP class that we defined further up. For classification tasks, it's usually a good idea to use cross-entropy loss. The optimizer is going to be an atom optimizer. Here we pass in the model parameters as well as the learning rate. And the data loader will be constructed out of the training data set. And here batch size is our hyperparameter. We also want to shuffle it because the way we constructed that mock data, it's a little bit sorted. So we're going to shuffle through that. And then we run through each of these epochs, and we're going to run through the full data set. Each epoch, we're going to get our axes and labels, put them onto the device in case that's the GPU. And then it's a typical to, zero the gradients, make the prediction, compute the loss, and then run these optimization steps. So this is how the model actually learns. And then if we run into a certain number of epochs where we want to calculate the validation loss, we're going to call this function that we defined above, run it on the validation data set, and then just print out what the validation loss is. And after all these epochs have run through, we want to print out the confusion matrix. So that's what this function does, as we've defined it further up, and then we print it out. And then usually we can just let it return the model, the fully trained model. We're not going to use it in this example case, but this would be a nice way to actually then use the model afterwards. So I'm going to run this cell. And now here, I'm actually calling this train method that we defined here. So I'm going to first run it with 10 epochs, learning rate of 0.01, batch size 32, 2 hidden layers of 4 neurons. In this first run, I'm not going to do batch normalization, and just because we have so few epochs, I'm just going to print out the loss after each epoch. So now I'm running it, and here it prints out, right? Epoch 0, this is the validation loss. And you see it's coming down bit by bit by bit until the very last epoch. And then this is our confusion matrix, right? So 201 times we predicted correctly outside the circle, 205 times correctly inside the circle, and these are the false predictions that we made. Let's do one little experiment on hyperparameters. That is, we leave all the hyperparameters the same, but we actually do the batch normalization right now. So I'm going to run this, and just at first glance we see, we're even starting out at a lower loss, so that's great. Yeah, it looks like our results have improved. And now this sets us up for hyperparameter tuning, right? So we could run this method, this function so many times and make all kinds of tweaks: learning rate, batch size, the architecture of the neural network, and really just kind of tune it. We can tune it naively, or there's also hyperparameter tuning strategies to apply here. This is something I might cover in a future video, but this should give you a good overview on how to apply a deep learning training flow. Again, you'll find the code for this in the description of this video on my GitHub page, and I hope you found this useful, you enjoyed it, and I also hope to see you in one of my future videos. Thank you. Take care.